Hello, so far in our code, we implemented absolute positional embedding, something similar to what is used in VIT paper. In this video, we are going to go over relative positional embedding. First, we are going to talk about an example to clarify the concept, and then we implement that in the code. Okay, let's start. Now we want to talk about relative positional embedding. And for relative positional embedding, first let's see how is that different from the absolute positional embedding. In VIT, we have absolute positional embedding, and we showed that, for example, how that looked like for different patches. And if we look at one example, for example, for a window size 3, I have these 9 elements. And if I want to create absolute positional embedding, I need 81 elements. I need to create a one matrix like this, 1 1 1 2 1 3, with respect to 1 1 1 2 1 3, and I need to define one parameters for each one of them. So the size of the absolute positional embedding is gonna be 81. It is window size to the power of 2, which is here 9, and window size to the power of 2 here 9. 9 by 9, I need 81 parameters. Now let's look at the relative positional embedding. And we are gonna have a matrix like this, and in this matrix, just imagine that this is a 9 by 9 matrix but has 2 channels. So for example, if this is X and Y, you can think that it has a depth 2 that you can see here. I'm showing 2 numbers. This is for the first channel, this is for the second channel. Okay, this is for first channel, second channel, and so on. And let's see what is meaning of that. For example, this green zeros that you can see here, that means that I am in the first row. So 1 1 with respect to 1 2, they are in the same row. So the row is not changing, but the column is changing. 1 1 with respect to 1 1, it is 0 0. But with respect to 1 2, it is in the exact same row, but 1 column forward. Next one, 1 1 with respect to 1 3. It is same row, 2 columns forward. Now let's look at the next line. 1 2 with respect to 1 1. 1 2 with respect to 1 1. They are at the same row, so it's gonna be 0, but 1 1 is 1 column behind, so it's gonna be -1. The next one, 1 2 with respect to 1 2. So that's the exact same location. Same row, same column, 0 0. 1 2 with respect to 1 3. From 1 to 1 3, we just need to go 1 column forward. So it's gonna be 0, +1. Now let's look at this one. 1 3 to 1 1. Same row, 2 columns backward. 1 3 to 1 2. Same row, 1 column backward. 1 3 to 1 3 is 0 0. Okay. Now I have this 3 by 3 with channels 2 that describes how this row is connected to each other. Okay. Now let's look at this green submatrix here, which is relationship between 2 1, 2 2, and 2 3. That is the exact same thing. So if you look at that, that is similar to this one. Also for this one, 3 1, 3 2, and 3 3 for the last row, you can see that is similar. So in a relative manner, they are similar. So we don't need to replicate these parameters. We just need to create one of them. Let's look at another submatrix. So we can see here this blue one. So blue one is a relationship between 1 1 and 2 1. So 1 1 2 1. It's gonna find the relationship between 1 1 and 2 1. So first you need to go 1 row down. So the row is 1. Column, same column. 1 1 to 2 2. 1 row down, 1 column forward. 1 1 to 2 3. 1 row down, 2 columns forward, and so on. And you can see that this blue submatrix is also repeated here. Then we have this yellow one. So yellow one is 1 1 to 3 1. 1 1 to 3 1. I need to come 2 rows down, same column. 1 1 to 3 2. 2 rows down, 1 column forward. This one 1 1 to 3 3. 2 rows down, 2 columns forward. How about, for example, this one? This one is 1 3 to 3 1. 1 3, which is this one, to 3 1. That is 2 rows down, 2 columns backward. This one 1 3 to 3 2. So that is 2 rows down, 1 column backward. And 1 3 to 3 3. It is just 2 rows down, same column. Okay? Let's look at this one, this red submatrix here. So it's a relationship of a 2 1 to 1 1. In terms of rows, it's a 1 row above that. So we are gonna put -1. And column is same. So column is 0. 2 1 to 1 2. 2 1 to 1 2. It is a 1 row. Before that, it's gonna be negative and 1 column forward. 2 1 to 1 3. It is 1 row backward, 2 columns forward, and so on. And we can see we have another red matrix here that is again similar. And then we have this orange one. Let's look at some elements of this orange one, which is 3 1 to 1 1. 3 1 to 1 1. So it is just 2 rows down, same column. 3 1 to 1 2. It is 2 rows down, 1 column forward. And 3 1 to 1 3. It is 2 rows backward, 2 columns forward. Okay, now let's count how many parameters we have. For example, in this submatrix, this green one here, so let's count how many parameters we have. Some of them are repeated. For example, 0 0 0 0 0 0. We have 3 0 0. We don't need 3. Only one of them we count. So we have 0 0 1, 0 1 2, 0 2 3, 0 -1 4. This one is repetitive. This one is repetitive. This one 0 -2 is 5. This one is repetitive. And this one is also repeated. Okay, total number of parameters in this green submatrix is 5. And how many different submatrix we have? So let's count the colors. So I have green, blue, yellow, red, and orange. So I have only 5. So 5 times 5 is 25. So by having 25 parameters instead of 81 parameters, I can fully define the relative relationship between all of the elements in this matrix. The other way that we can interpret this number of parameters is this. If you look at the different colors in this big matrix, you can see we have 5 different colors. And each color represents a different row. So for example, if it is green, it means that we are at the same row. If it is blue, it's +1. It means that is a 1 row forward. If it is yellow, it means 2 row forward. -1 for the red one is 1 row backward. And -2 orange one is 2 row backwards. So basically, to find the relationship in the row direction, I need 5 parameters. And in the column direction, we also need 5. For example, here in this submatrix, we are at the same row. What we showed that we need to go 2 forward or 2 backward. So overall, we need 5. So 5 were the rows, 5 were the column. So we multiply, we get 25 parameters. One advantage of using relative positional embedding is shown here that we are reducing the number of parameters. For example, for a very small window, for window size 3, we showed that from 81 parameters, we could get to 25. And you can imagine when your window size is bigger, you are saving more parameters. So we are not going to use that. Also, they showed in the paper that using relative positional embedding, they got the better results. So let's go back to the paper and look at that. Okay, if we look at table 4, we can see absolute positional embedding here and relative positional embedding compared, and we can see For example, for ImageNet, they got better results for top 1 and top 5, and also for the other datasets. Okay, so because of these two reasons, first is going to give us better results, and also with lower number of parameters, we are going to use relative positional embedding. Also, this relative positional embedding that is introduced in Swin transformer paper is used in a more recent paper. For example, in Vision GNN, they are using the same idea. And if we go on page 5 of this paper, we can see that they are mentioning that they are using the relative positional encoding or embedding, and they're following what Swin transformer is doing. So they also try to follow Swin transformer and use the success of relative positional embedding compared to absolute positional embedding that was originally used in VIT. Okay, let's go to the code and start implementing that. Okay, now we are going to come back to our window attention class and try to modify our code to enable it for relative positional embedding. So instead of this line here, now we are going to have this. Okay, if relative positional embedding is true, so we are going to have these two lines. And if it is false, like past, we just go for absolute positional embedding and use the exact same line as past. But if it is true, we need to have a number of parameters defined. So number of parameters for positional embedding now is 13 by 13 because our window size is 7. So 2 times 7 is going to be 14 minus 1 is going to be 13. So it's going to be 13 by 13. And if you can imagine like this, that if you have one element in the your window which is 7 by 7, that one element, you can see 6 possible relationships to the nodes on the left and on the right. So 6 to the left, 6 to the right is going to be 12. Its relationship to itself is going to be 13. Also for the top and down. So 6 on the top, 6 on the down, and itself. So it's going to be 13. So overall, I need 13 by 13 parameters to fully define all of the relationships. But these 13 by 13 parameters, these are just number of parameters, not the big matrix that we need. So just like here, we need a big matrix to put these parameters in. And our big matrix for relative positional embedding for window size 3, it was still 9 by 9 and had 81 locations to put these parameters in. So this time we are creating a big matrix which is 49 by 49, and then we put those 13 by 13 parameters inside that. Okay, so this line here is just creating 13 by 13 parameters, and this line is gonna create that big matrix that we are gonna put the elements inside that. So for this line here, I need to use a function called getRelativeDistances. Let's start writing this function. Okay, this is gonna be our getRelativeDistance function. The input to that is our window size, and then you define indices here, which is basically something like this, which is a 49 by 2. It has 49 elements, and for example, first element is 0, 0, the second one is 0, 1, and so on, all the way to 6, 6. And using this trick, you should be able to create what we are looking for. So for example, for window size 3, if we do that, we end up having this matrix, and this is exactly what we are looking for. For example, this is the second channel of that. Let's look at the first channel. For example, you can see we created the exact same matrix. So you can see that for the first 3 rows and 3 columns. So for this sub matrix, so we have this green that we have here. So this one here, we created here. Again, this one is 0, 0, 0, and this one. So you can see that is identical. So using this function, we are able to create this. Let's look at the second channel of that. So if we look at the second channel, we should see these pink values. Okay. Also, we can see for the second channel, we see these pink values. For example, for this submatrix, we can see 0, 1, 2, minus 1, 0, positive 1, minus 2, minus 1, 0. Okay, so this is going to create the matrix that we need as the positional embedding. To get a better understanding of this line here, we can also look at the one numerical example. For example, so we could have one tensor like this, and then we can print A and look at its size, and then we can do something similar that what we did here. We can add the none to the first dimension and print out the size of that, and for A2 we add none on the second dimension and we can print the size, and then we can conduct this A minus A2 and see the size and D. Let's do that, and we get this one, and you can see that A is originally this, the size of that is 3, and then we added one dimension and now it is a 1, 3, and A2 is this one, A2 size is 3, 1, and if we say A1 minus A2, the resulting tensor is going to be this one, and that is 3 by 3. So this is very similar to what we did here. So for example, this one is the submatrix here, but here we have more dimensions. We have, instead of having only 1, 2, 3, each one of them has 2 dimensions. So the resulting matrix is going to have 2 channels. So first channel, as we showed, is going to be this one, and the second channel is going to be this one. And this is exactly what we need for our relative positional embedding. Okay, let's go forward. So in our window attention class, we said that first we initialize this relative positional embedding that we did here, and now we are going to use that in the code. So let's go forward in the code, and instead of this line here, now we are going to have this. Okay, now we are going to have this section. Okay, let's look at the details of this section. We are going to say if relative positional embedding is false, we are at else, and we do what we did last time. So we are going to be in this section of the if statement. But if the relative positional embedding is true, we are in this section of the code. We can see that first we have this position embedding, which is a 13 by 13 matrix that we have all of the relative positional embedding parameters. We said that because we have a window size 7, so we consider 6 elements on the left, right, and itself, so it's going to be 13, and up and down each one is going to be 6 and 6, and itself is 13. So we need overall 13 by 13 parameters. Okay, that is this position embedding, and we initialize that already here. So here we initialize that as a 13 by 13 matrix. Okay, so we have that one, and the other one that we have is this relative indices, and this relative indices is the big matrix that we created, that is basically this one. Okay, so for our example, because window size is 7, it's gonna be 49 by 49 with 2 channels. So for example, if we get the size of the first channel, that's gonna be the 49 by 49. Okay, then we do this. We say self.position embedding, and then we have first the indices of the first channel, and then we are going to have the indices of the second channel. So the result of this section is gonna be a 49 by 49 matrix. Okay, let's look at one numerical example to get a better understanding of this section. Okay, let's consider this numerical example where our positional embedding, instead of being 13 by 13, is just a 2 by 2 tensor, and you can see the size of that is, for example, printed here as 2 by 2. And then instead of our relative indices, which was 49 by 49 with 2 channels, now we have this R, which is basically 3 by 3 by 2 channels. Okay, and then similar to what we have in the code, we are gonna have this line. And let's see what is gonna be the output. The output is this one. So the size of the output is 3 by 3, similar to what we see in the code, which is 49 by 49. And if we look at the variables inside the matrix, for example, for the first element, we can see because here that is 0, 0, it means that that's gonna be the parameters 0, 0 in the position embedding matrix. So that's gonna be 1. So 1 is gonna be here. So the next one, again 0, 0, it's 1. The third one, 0, 0, 1. This one, 1, 1. What is the positional embedding 1, 1? That is this one. That's number 4. So this one is gonna be number 4. Again, 1, 1 for the next one is number 4. For the third one, number 4. 0, 1 means first row, second column. First row, second column. Value is 2. So value is gonna be 2, 2, 2. So you can change these numbers. For example, you can have here 1, 1 or here 1, 0. And if we run it, we can see we can get different elements from this positional and embedding parameters. And this is exactly what we are doing in our code. So we have this positional embedding here, which is 13 by 13. And we have all of the learn number parameters inside that. And then in our relative indices matrix, we are going and telling which parameters we want to read. And basically that is this matrix, that which parameter we want to read. And at the end, when we use that here, we ended up having 49 by 49 matrix, and the elements of that matrix are coming from that position embedding matrix that originally we created. Okay? The other point that we should consider here is that these elements inside our relative indices matrix, they need to be valid indices that we could get the value from the positional embedding. For example, I can't have a value 2 here because 2 is not a valid index when I have my matrix is 2 by 2. So I only can have 0 or 1. Okay. And because of that, when we are creating our relative tensor, we make sure that indices are in a range that is meaningful for us. And because of that, when we initialize our relative indices here, we made sure that here we put the indices in the correct range by doing this. So by adding the plus window size minus 1. Okay. For example, if we don't do that, we see this one. Okay, let's consider this matrix. This matrix is the relative indices matrix for a window size 7. So for window size 7, you can see I have 0, 0, 0, 0 in the first channel because we are in the same row. And sometimes we have negative row because, for example, where I am here, I have 6 rows above. So I have to have negative values, similar to what we have here. So here, for example, you see I have minus 2, minus 2, minus 2 in my first dimension. Okay. But we can't have negative when we are working with indices and we want to read those indices from positional embedding matrix. As the result, we added plus window size minus 1. So we are going to add 7 minus 1. We are going to add 6 value to all of these elements. So we ended up having this one. And you can see the indices are 0, 1, all the way to 12. And those are the indices that we can read from our positional embedding matrix, because positional embedding matrix is a 13 by 13. So indices are between 0 and 12. Let's look at the second dimension. So second channel in this matrix is shown by pink color, and in the same fashion, we are gonna have a second channel for our matrix. For example, this is our second channel for a relative matrix, and you can see here I have values that are between positive 6 and minus 6. Again, I just need to add window size minus 1. So I need to add 6 to all of these elements. And if we do that, we ended up having this one. Now all of the elements are between 0 and 12, and we can easily use those indices when we are reading from positional embedding matrix. Okay, let's look at the code again. And whenever relative positional embedding is true, we said that this section is gonna be 49 by 49, and we plus that to dots, and the output of the dots, the size of that is gonna be this one. So it's gonna be batch size, we have the heads, we have the number of windows, and the size of that is gonna be 49 by 49. And the output of the dots is identical as the output of the dots when we have the absolute positional embedding. Okay? Okay, now we have our relative positional embedding ready. Let's run the code again to see if it works. So let's run all. Okay. We should be able to get the output, and yeah. So we are able to get the output and it works. So now we are done with relative positional embedding.